Hi everyone, James again. I do want to point out that it's like early on a Sunday morning, so if I'm a little bit slow, that's why. And also in the description of the last video, I was sure to point out that you might want to watch it in double speed because, I don't know, the way I'm going about it, I guess, with these problems is not really rehearsing and trying to basically do the problem in real time rather than having it all written out and following step by step and just doing it fast through. Or another way of doing the problem, I guess, would be to just like have it all written out already and then me just read through and be like, okay, I did this and I did this and I did this, and then, you know, I don't know, I feel like it's more natural this way, but whatever. Really, this is probably not going to be seen by anyone, and it's more just for my own reference, so I prefer to have it like this, I think. Anyways, 1.2, the problem is basically the same as last one, except you're using the regularized sum of squares error function. I guess I'll write that. So it has a tilde because it's regularized. I believe that's right. Okay. So this is obviously E of W and again, the way that we want to minimize this function and find the parameter vector that minimizes the function, take the gradient with respect to the parameter vector, set it equal to 0. Physically, what's going on, similar to the little plot that I drew last time. So this was the plot last time, something convex like that, where that looks weird. It's always positive, it's quadratic, so you can find a point at the bottom where the derivative, in this case the gradient, is equal to 0, and that's the minimum error. Now we're just basically shifting the points based off of the size of W. So we're penalizing large parameter vector values. So if you think about what this value would be, it would basically be something like that, right? So if you're just adding those two functions, the regularized error function, it would just basically be this, and then you would shift everything but you'd shift it up more as you got away from, as you get further away from the origin, because these values are larger. So you have a function like that. So it's a little bit different, but it's still convex, basically. And the minimum would be different. It would have a smaller parameter vector weight, basically, as this, you know, like the minimum before was over here, and now it's over there. Okay. But the minimum can still be found by taking the gradient with respect to the parameter vector w, setting it equals 0. I think it's always good to try to think of the thing physically and not just do the math. Just because, I don't know, you can get lost in the equations, you lose track of what exactly you're solving for, or why you're solving for it. Alright, so taking the gradient of E tilde, it would be the same thing as taking the gradient of E plus the gradient of the second term, just because, you know, derivative or gradient it's basically a linear operator. So if you're taking the derivative of a plus b with respect to x, it's the same thing as taking the derivative of a with respect to x plus the derivative of b with respect to x. It's a linear operator, so you can separate those out. Thankfully, we already have this, right? Derivative of, or gradient of e with respect to w from the last problem. And all we need to do is basically find the gradient of the second term, the penalization term, with respect to w. So if you think about what this term actually is, that's what that is. If you think about, so you're taking the norm of that vector, of the parameter vector. When you take the norm, you're taking the square root of all the elements squared. The square root of all the elements, of the sum of all the elements squared. And if you square that, you basically just get the sum of the elements squared, which is what that is. And you're multiplying it by the regularization term, lambda divided by 2. And so yeah, taking the gradient of this with respect to the parameter vector, again, you'd be writing it, it's a vector. So you're taking the derivative, or the partial derivative of lambda over 2 w norm squared partial with respect to W0, that's the first element. Taking the partial with respect to W1, second element. Taking the partial with respect to Wm is the last element. So it's an element, a vector with n plus 1 elements. And basically, if you think about taking the derivative of this expression with respect to W0, you would get 2 times W0 times lambda over 2. Because all these other terms would be considered constants because there's no W0 in them. Take it, the partial with respect to W1, you'd get 2 times W1, and then you'd still have the lambda over 2. Take the partial with respect to Wm, you get 2 times Wm, still have the lambda over 2. Alright, so basically you just get lambda times a vector with all the W elements. And that is the gradient of, the second term in the regularized sum of squares error function. The gradient with respect to the parameter vector. And now you just add that into the equation that we had from 1.1. Which I don't really feel like deriving again, so you can just look at that video, hopefully. Let's see if I can remember it. Get T on the right hand side, get Aij times W on the left hand side. I'm just trying to work in what we just found into the system. Really we would have the vector of W values, but we want to write in a similar format. This is the gradient of E with respect to W parameters. I believe. How would you work that? I don't think you could work this into that factor, but maybe I'm wrong. I don't know. I think you would just have to find another W in terms of I. Just to make sure I does run from the same indices, right? 0 to M. I think that's how you do it. I'm not sure if that's how they put the solution in the textbook. Yeah, this problem doesn't have a solution online, although it's probably on Chegg or something. But I'll define IA and T. What's our next? Yeah, that's next. All right. All right, so yeah, I think that's, I believe that's correct, and I'll probably check and confirm, and you probably won't see this if it isn't correct. So maybe you will, and I'll just be too lazy or whatever. This problem, it's a 1-star problem, so it's supposed to only take like 5 minutes according to Bishop, which is funny, but I suppose if you were writing it down and weren't talking it out, it would. But yeah, I think that is correct. Thank you very much for watching. Get you in the next one. Don't depend on me for correctness, by the way. I just want to reiterate, I would feel bad if someone like took this as gospel and I'm just trying to work this out, same as anyone else, really. And really, what I'd want, I mean, it would be awesome, is if a bunch of people also had videos on the subject, but not realistic. And so, anyways, hope this helps. Thank you.